Hello! So in this video I want to talk through something called the method of successive approximations. And actually it's kind of linked in with something called the existence and uniqueness theorem, which we've looked before. You know, if I remember, it was like an hour-long video. It's ridiculously long. But I sort of said that, you know, the main important elements of that video were kind of covered in the first 15 minutes. So if you get what was proposed in the first 15 minutes, then you can kind of pretty much follow the existence and uniqueness theorem. But this is actually kind of like, if you like, what would, in an exam situation perhaps, this is kind of linked to the existence and uniqueness theorem. It's called method of successive approximations. If you remember, we did look into method of successive approximations when we were doing existence and uniqueness theorem. But here we're actually going to use method of successive approximations to try and find a solution of an ODE, except we're not, okay? But I'll kind of come on to I'll kind of elaborate on what I mean by that in just a moment. So, okay, so what is the method of successive approximations? Well, if you remember, okay, well, you know, say if we have a first order ODE of this form, okay, it may or may not be linear. So in other words, we can write a first order ODE. So remember, a first order ODE is the first derivative plus, some constant, which could be variable, times by the function which we want, and that's going to be equal to something involving t on the left side, on the right hand side, if t is our independent variable. Okay, well, basically the idea is that we can rewrite that in such a way, that we end up with the first derivative on one side, and then on the right hand side, we just end up with something involving y and our independent variable on the right hand side. So our function, our independent variable on the right hand side, it'll be a function. And like I say, this may or may not be linear. It could be non-linear. It works in just the same way. Okay. Well, okay, let's rearrange this. So I'm basically just going to write y dash. At the moment, y dash is the first derivative. I'm just going to write that in the form which you're probably more familiar with seeing it in, which is dy by dt. So I'm going to rewrite that as dy by dt. So dy by dt is equal to the function of some function which involves y and t on the right-hand side, which may or may not be linear. It may also be non-linear as well. Okay. So basically, the idea is that say if I have something like dy by dx is equal to 4x. Okay, well then fairly obviously you can find out what y is. You can find out what y is just by integrating. So y is equal to the integral of 4x with respect to x. This is the idea that integration and differentiation, it's kind of linked to the fundamental theorem of calculus, which basically says, it says other things as well, but it kind of says that differentiation and integration are opposite processes of each other. Okay, so if we use a similar kind of idea here, okay, then basically we can work out what y is equal to, right? Because if the derivative of y is equal to some function involving y and t on the right-hand side, then y is just going to be the integral of whatever's on this right-hand side. Oh, sorry, there's a y and t on the right-hand side with respect to t. Okay, so hopefully, you can kind of see where that's coming from. Now, and of course, there will be some constant of integration. There will be some constant of integration which kind of comes out from that. Now, the reason why I'm writing the constant of integration now is because we can actually kind of deduce what that constant of integration is going to be. Because with method of successive approximations, we will be given some initial conditions. So what do I mean by initial conditions? I've spoken a little bit about what initial conditions mean before. In general, when we solve an ODE, we can have millions of solutions. Yeah, they'll all look the same. So this might be, if we have something like this, it may look like a solution like that. Okay, but we'll have millions of them, which will all look the same shape. Okay, but they'll just be at different points. Okay, they'll just lie at different places on the graph. So in order to work out which one corresponds to the ODE which we're looking at, we need something called initial conditions, if you like, just to pinpoint a particular point. Yeah, so say for example we might have an initial condition that y 0, so when t is equal to 0, then y is equal to y naught. Okay, so this is basically what this is saying. Y, when t is 0, is equal to just some number, some value, which is y naught. Okay, and basically, say if that corresponds to y naught there, and that corresponds to t equals 0. Oh, that doesn't correspond to t equals 0. That's 0 over there. So maybe it will correspond to something over there. Sorry, I've perhaps not made that clear. But essentially, what we can do is, given 2 points, yeah, we can basically, pinpoint exactly which graph we want. And that is what method of that's basically what an initial condition does. I've spoken about that before, so I've gone through that fairly quickly. Okay, so basically the idea is that if we have an initial condition like that, okay, then we can try and work out what this c is. Okay, and I'll try and show you how we can do that. Okay, so what we're going to do is we're going to look at this thing here. We're going to look at this thing here. And actually I'm going to look at it in a little bit more detail because there's something else which I can add in there. Essentially what this is saying is that the solution which we want is going to be the integral of that, okay? And the idea is that it's going to be method of successive approximation. So we're basically going to try and, it's a numerical solution. So the idea is that we put some value into, our function. So in this case, our function is this thing here. Okay, basically we'll put something into our function and we'll get an output out. So this is an output and this is an input, okay? And then basically what we do is we take that output and we put it back into the input, okay? And then we do the same thing again. So if you like, we're forming this loop. And that's kind of what a numerical solution is. It's an iterative process, yeah? So we use the output and then that becomes the input. And then basically what that has the effect of doing is converging into the exact point that we want. In this case, the exact solution that we want. Right, so basically, just by doing this kind of loop, we can converge towards the solution which we want. And how do we know we've reached the solution? Well, when we put an output in, okay, so we use this output and we put it in for the input. Okay, well then when we get the same output again, so the same output as we put in. So in other words, these two things will end up equal to each other, then we found the solution which we want. Or, when they're roughly equal to each other, then we found the solution which we want. Okay, well that will all happen over some time interval. That was all happen over some time interval. So if we define that this function will occur over some time interval, for example, if I just try and use an analogy, if we have a function like this, okay, and we want to converge towards a particular point. So say, for example, we want to converge towards that point there. We always have to start in some finite time interval. So say, for example, we go from t1 to t2. Okay, if this is a t-axis. Okay, we might start from there, and we go up to there. And then basically the idea is that we approach from both sides, and we approach that particular point there. Okay, so in other words, what I can say is that I can put some limits on this integration. Okay, so I can go from 0 to t. Okay, so naught is just a conventional because I can start anywhere, right? I can start anywhere down here, so it kind of makes sense to start at 0 because normally when you plug stuff in for 0, things tend to cancel and it tends to look quite nice. Okay, so let's just start at 0 and let's just go to some time interval t. So hopefully you've kind of followed that analogy. Maybe, but of course, then we can take an advantage of something called the dummy variable. Because remember, a dummy variable, all dummy variable is, this variable in this integration, or this integrand, I suppose. The integrand is the thing which we integrate. It doesn't matter what I call it. At the moment, I'm calling it t, so I'm integrating with respect to t. Yeah, but it doesn't matter what I call it. Okay, so I'm going to just change it because my limit is t. I'm just going to change this letter in here, and I'm just going to change it to s because I can. Yeah, I can call it anything I like. The point is, let me just try and show you. If I integrate t squared with respect to t, okay, well then that's obviously going to be, what's it going to be? A third t cubed, right? But then if I integrate x squared, say, with respect to t, well what's that equal to? It's going to be a third x cubed. If I integrate s squared with respect to t, that's going to be still a third s cubed. Yet the point is that the right-hand side will... sorry, that's not quite right. The right-hand side will always look the same. The right-hand side will always look the same. It'll just be different variables each time. So in other words, the variable doesn't have any impact on the integration. Yeah? It's kind of like as long as these two things are the same, as long as you change everything. So in this case, I've changed my t to an s everywhere, then that's fine. And the reason why I've done that is because this limit here is a t. Right, so when I put that t back in, when I evaluate the integral and I put that value for t back in, then there's a risk that I may get confused because, of course, I'll end up with something involving t and then I'm putting in a new value of t back in. Well, why not just change the original value for t to s? Yeah, it makes so much more sense. It sort of stops you becoming confused. So that's where the idea of limits come from. Hopefully, you've followed that. Okay, so now we basically got everything that we need. Okay, if we now use this initial condition and basically say, well, okay, when t is equal to 0, because that's what that thing in there is saying, y of 0 equals y naught. The of 0 part means that when we set t equal to 0, we get y naught out. Okay, so in other words, in this thing here, okay, if I now evaluate t at 0, so let me just write it out again. Okay, so in other words, basically when I'm subbing subbing t equals 0 into this, because this is exactly the same thing as what I've just written out. Just because this thing here is dependent on t, because of course my integral will be dependent on t. So therefore this will be dependent on t. So that's what I normally just admit that because it kind of gets in the way. But yeah, this is exactly what this is. So basically, if I replace t with 0, then I've got to replace all t's with 0. Okay, and now you can see why I've used the dummy variable, because the temptation, if I'd left this as t in here and t here, I would have, the temptation would be to replace that with 0 as well, which of course isn't true. Okay, so that's where the dummy variable kind of comes into its own. When I sub a value back in, then obviously, obviously kind of I don't get confused, hopefully you can see that. So basically what is this saying? Well, when y is 0, so I know that this is equal to y naught, right? Because y of 0 is equal to y naught from this thing up here. From this thing up here, I know that y of 0 is equal to y naught. So when I sub t equals 0 into this thing, I should get y naught. Okay. Well, what is this basically saying? I'm saying that the integration from 0 to 0. Okay. Remember what integration is saying. Okay. The integration is the area underneath the curve. So in other words, if I have an area underneath, say if my curve looks something like this, okay, and this is 0, and so basically what I'm doing is I'm finding the area underneath the curve. So say if it was from 0 to t, say if t was over here, then I'm finding that area underneath there, right? But what this is saying now is that I'm finding from the area under the curve from 0 to the same point 0. So in other words, I'm not moving. So I'm just finding that line there. Well, what is the area of a straight line? It's 0. So this integration in here is 0, okay, because I'm going from 0 to 0. Given these initial conditions, this is 0. So in other words, what I can now say is I'm left with, when y is 0, I just get c, which of course is just y naught. Okay, so in other words, I've just worked out what my value for y naught is given these initial conditions. From these initial conditions, I've now just worked out what my value of c is. Okay, it's y naught. My value of c is y naught. Okay, because I've just worked this out. Okay, so hopefully that makes sense to you, that, now what I can say, if I just write this out formally, so now what I can say is that method of successive approximations gives me the formula that y of t is equal to the integration over some limit from 0 to some value. These are the limits which we choose, because of course, it doesn't matter where we start from. With the method of successive approximations, the whole idea of method of successive approximations is that you kind of start from one end and start from the other, and you kind of gradually converge closer and closer and closer towards the point which you're after. So basically, as long as you start within some reasonable interval, so as long as you start from, say, some large enough interval, which you define, yeah, and as long as you know that the point which you're after is inside that interval. Of course, the point here is kind of, I'm using this as an analogy because we're not after a point anymore, we're after the function. But anyway, it's the same kind of principle. Then basically what we can just say is that, we go from 0 to some value t. We just start at 0, let's say, and let's go up to some value t, okay, because that's the interval that we think the function is going to lie in, okay. That's going to be equal to f, so some function involving, this is just the right-hand side, effectively, involving y, and of course y is dependent on t as well. This is just a function which is dependent on t, okay. The t at the moment, but of course I'm going to change these to dummy variables, so they're dummy variables, so I'm just going to change them to s, just to make things easier for me and to ensure I don't get confused. Okay, plus then c, which is then my y naught. So in other words, what I can say is that this thing is equal to this thing here. I've come up with a formula for successive approximations. Now, just very quickly, alarm bells should be ringing in the back of your mind, okay? Because what is this basically saying? Well, if you think a differential equation, if you just go back up to here, what this is saying is that the first derivative is equal to something on the right-hand side, which involves y as well. Yeah? So that's the reason. You may say, you may look at that and you say, well, why don't we solve first order differential equations like that? Well, the answer is because it's not strictly true. Okay, what we're basically saying here is that y is equal to the integration involving something involving y. So in other words, our solution will also lie on the right-hand side. Okay, so we're integrating something which involves our solution, which clearly we can't do. So why then would we bother doing this? So, if you're faced with an ODE, you would not go about solving it in this way. If you wanted to find a solution to an ODE, you wouldn't go about solving it in this way. So why are we looking at this? we'll think about the existence and uniqueness theorem. All we're interested in is whether the solution actually exists. Okay, that's the first thing we're interested in, and then we're interested in how many there are. So in other words, is there only one solution given some initial conditions? Given some initial conditions, is there only one solution, which we have to find? Okay, and this is basically what this formula is saying. Okay, this formula is basically telling us whether there exists a solution. And because we've actually defined C as y naught from our initial conditions up here, then basically what we're saying is that, given some initial conditions, we can determine whether there's actually a solution which exists in the first place. Because of course ODEs can be quite difficult to solve, particularly non-linear types. We kind of steer away from them, or some of them in this course. We look at some special cases, but in general we kind of steer away from them. So basically what we're doing with this method of successive approximations is we're seeing whether one actually exists and how many there are. Yeah? Because of course, given some initial conditions, as long as one exists, then there's only one of them. Okay, so as long as there's a solution that exists, because it's defined by some initial conditions, then by the existence and uniqueness theorem, then there's only going to be one that exists. Okay, so hopefully that makes sense. We wouldn't go about solving the ODE like this, but we'd use this method to give a good indication of whether one actually exists or not. Okay, so basically what I'm trying to say is that the answer that we get out from this thing, so when we evaluate this thing using the method of successive approximations, the value that we get out isn't necessarily our function. But if there is an answer that we're getting out, that's what we're interested in, whether there is actually an answer that we get. If there is an answer that we get, then therefore we can clearly say there is a solution, and therefore it's worthwhile solving this ODE in the first place. Okay?